Mr. Brown gave a test to his very large class. And after he was done grading the tests, he decided that he wanted to represent the grades somehow so that he could determine how well his students did. So his decision was to make a dot plot. Now with a dot plot, we start with a number line, and we divide that number line into equal intervals, and then we place a dot on the number line representing each of the grades. If we have more than one of the same grade, we stack the dots on top of each other. So what Mr. Brown noticed when he built his dot plot was that the grades seemed to be forming a particular shape. The shape that he was seeing is something called a normal distribution. Sometimes a normal distribution is called a bell curve because it kind of resembles a bell. What's always true about a normal distribution is that the mean, meaning the average of all the data, the median, meaning the data value for which half the values are above and half the values are below, and the mode, meaning the data value that occurs the most often, all three of those are identical. The other thing that's always true about normal distributions is that they are symmetrical. So you can imagine that if we folded this picture along that line where the mean, median, and mode are, that the two sides would match. So if we think a little bit more about this normal distribution, we'll notice that pieces of it can be identified as having a particular percent of the data values within that piece. So how do we know where to divide these pieces? Well, we need to know two things. One is the mean. So let's suppose that Mr. Brown's mean test score was 75. And we also need to know the standard deviation of all the scores. In this case, let's suppose Mr. Brown's standard deviation on the test was 5. Now, if you look at the 75 and you go 5 higher than that, up to 80, you're within one standard deviation of the mean. So what that tells us is that all the test scores that are within one standard deviation of the mean to the right of the mean, 34% of the test scores fall in that range. Now we can continue that and go another standard deviation further from the mean, and we can see that between 80 and 85 is where 13.5% of the test scores will fall. And we can continue that until we get to 3 standard deviations above the mean. That's a 90 in this case. And anything above that is only 0.15% of all the test scores. Now, since this curve's symmetric, we can also go the other direction. So to the left of the mean, we have 34% of the scores between 75 and 70. And we can continue that by subtracting 5 from 70, and we'll find that between a score of 65 and 70, we had 13.5% of the test scores, and so on. So, what percent of the test scores were between 75 and 85? That means we're looking for the percent of the test scores that fell within this range. You'll notice on the number line, we're looking at everything from 75 to 85, and we want to know the area under the curve between the 75 and the 85 test scores. So if we add together the 34% that's between 75 and 80, and the 13.5% that's between 80 and 85, we get a total area of 47.5%. Well, what if we want to know what percent of the test scores were greater than 70? Once again, looking at that number line, we're looking for all the test scores that are 70 or above. So we want the area under the curve from 70 all the way to the right-hand side. Now what we could do is add together the 34, the 34, the 13.5, the 2.35, and the 0.15. Or alternately, what we could do is recognize that because this curve is symmetric, that the area from our mean of 75 all the way to the right tail of this curve has to be half of the area, which means we want that 50% that we see in blue plus the 34% that's between 70 and 75 for a total area of 84%. So let's look at another problem. A 1981 survey of 20 to 29-year-old Canadian women showed their mean height to be 63 inches, with a standard deviation of 2.5 inches. Now, since this is a normal distribution, we can think of the areas under the curve exactly the same way as the last problem. The mean and the standard deviation give us a way to label the number line under the curve. So the mean is 63 inches, and since the standard deviation is 2.5 inches, we know that 63 plus 2.5, or 65.5, is a height that's one standard deviation above the mean. Another 2.5 added to that gives us 68, so that's a height that's two standard deviations above the mean. And another 2.5 added to that gives us 70.5 inches as the height that's three standard deviations above the mean. Now going to the left, we'll subtract 2.5 inches to get 60.5 inches for a height that's one standard deviation below the mean. Subtract 2.5 from that to get 58 as the height that is two standard deviations below the mean. And subtract 2.5 from that again, and we get 55.5 as a height that is three standard deviations below the mean. Now, knowing that, what percent of women were at least 65.5 inches tall? So looking at the number line, we can see where 65.5 is, and we want all the heights that are at least that. So from 65.5 all the way to the right-hand tail. Now there's two ways to get this. We could add the 3% that we see in the regions that are shaded. So 13.5% plus 2.35% plus 0.15% gives a total area of 16%. The other way we could approach this is to recognize that this area that we now have outlined in blue is half of the area under the curve. So that's 50% of the heights. Of that part that's in blue, we don't want to count the 34%. So if we take 50% minus the 34% that we don't want to count, we end up with the same 16%.